Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about the additional design problems on simply supported one-way slabs and two-way slabs. This may be a final last class regarding our slabs consideration. So let me recall what are the things we have discussed in whole chapter in brief. So what is the definition of slab is? What do you mean by slab? Slab is a two-dimensional element which can be used as a floor as well as a roof cover. And these slabs are categorized as based on their shorter span direction and longer span direction, that is one-way slab and two-way slab. A slab said to be a one-way slab when its longer span direction, I can say this is Ly, and shorter span direction Lx. This ratio is less than or equal to 2. I can say this slab is said to be a two-way slab. If this ratio is greater than 2, then we can call this slab is said to be a one-way slab. Then we have discussed in two-way slabs we have two more types. One is restrained slabs and unrestrained slabs. Restrained slab means corners of the slabs are not lifting up, and unrestrained slab means corners of slabs are free to lift up, and we have seen a design of those things also, right? So the design steps of one-way slabs and two-way slabs almost 50% to 60% are same. Then somewhere they may be differ. So those things were discussed already when we are designing one-way slab and two-way slabs. Say, let me recall the steps regarding one-way slabs and two-way common steps. Let me recall. First, in both the cases, we have to calculate what is the effective depth is. What is the effective depth? We have to assume small d is. And then we have to calculate effective length. In one-way slab is only one direction, that is a shorter direction Lx. And simply in the two-way slabs, we have to calculate effective length along the shorter direction as well as in longer direction. Then we have to calculate total load which is likely to occur on both the slabs. Say one-way slab and two-way slabs, we can calculate in same fashion. Say dead loads, we have to calculate live loads, given load and finishes. And if adding all together, we will get the total load which is likely to coming on the slabs. And if the total load are multiplied with a 1.5, then we will get what is the factor load is. So after obtaining the factor load, if we concern one-way slab, we have to calculate the maximum bending moment. That maximum bending moment here, when we are designing one-way slab, we are considering as a 1 meter width of a beam like we have considered. So when you simply, as you are designing a simply supported slab here, a simply supported slab is subjected to UDL throughout, then the maximum bending moment will be WL square by 8. So like that we can calculate the maximum bending moment for one-way simply supported slab. So whereas in case of two-way slabs, we can calculate the maximum bending moment in two directions, that is the x direction and y direction. There are some codal provisions for that. Based on the codal provisions, we can calculate mx is a maximum bending moment in x direction, and my is the maximum bending moment in y direction. And these mx values and my values are depends upon bending moment coefficients. So they are given in table number 26 and 27 of IS 456-2000. Based on that and based on the type of slab, we can choose that bending moment coefficient like alpha x and alpha y values. You know, the alpha x is the bending moment coefficient along the x direction, and alpha y is the bending moment coefficient along the y direction. So then after knowing how to calculate the depth of that, then we go for calculation of area of steel, that is AST. So AST can be calculated by using the moment of resistance formula or the moment of resistance formula with respect to the tension in your one-way slab, that is mu equal to, that is ultimate moment equal to 0.87 Fy AST into 1 minus Fy AST by FCK into BD. From that formula we can calculate the area of steel. That after knowing the area of steel, we go for checking of that we check with the minimum reinforcement required, then we go for spacing. The same thing with the case of two-way slab. Here we have to calculate area of steel in both the direction, and moreover these two-way slabs are divided into a edge span, middle span, and in x direction and y direction like this. So this is a slab, say this is the LX direction, This is the LX direction, this is your LY direction, and this slab will be categorized into these parts. That is, this is the edge, this is one more edge, and this is the middle one. So middle strip, we have to calculate area of steel in this middle strip direction and area of steel in the edge strip and in this edge strip. Similarly, the slab is also divided in small shorter span direction also, like edge span, middle span and edge span. So this is called again a middle strip region in x direction, and it is edge strip in x direction, and this is also edge strip in x direction. Like that, we have to divide our two-way slab. Those areas we have to calculate what are the area of reinforcement to be provided. Correspondingly, how much will be the spacing to be provided. Those things we will calculate. Finally, we go for checks like deflection, development length check and shear checks. So these are the things we have discussed so far regarding our one-way slabs and two-way slabs. Complete, I can say, regarding the slabs. Right? And we have solved so many problems on one-way slabs and two-way slabs, means analysis of one-way slabs, two-way slab, and how to design the one-way slab and two-way slabs based on the codal recommendation. So today the final class regarding slabs. So let me give some more examples on design of one-way slabs and two-way slabs. So let me explain the slab first. One-way slab. So the one-way slab is given here. Based on this condition, we have to design what is the one-way slab is. Okay. Based on that, they are given one problem that design a simply supported. What is that? Support condition is simply supported roof slab of for a room. For a single room, we have to design 8 meters by 3.5 meters in clear size, supported on what is the width of the size? What is the width of that support? 230 mm. And slab is carrying imposed load, that is 5 kilonewton per meter square. Here you have to use M15 grade concrete and Fe 415 steel. So in this problem, it was not mentioned that what type of slab we have to design. You know, the category of slab is classified based on the longer span ratio to the shorter span ratio. So the longer span is Ly, then shorter span is Lx. So Ly by Lx can be, if the Ly by Lx value is greater than 2, then we can design it as a one-way slab. If Ly by Lx value is less than 2, we can categorize as a two-way slabs. Say, let us see according to this problem. Say Ly is 8 here. I am considering it as a longer span because the dimensions are more compared to x, and shorter span direction is Lx, that is 3.5. If I take the ratio of Ly by Lx here, Ly equal to 8 and Lx equal to 3.5. If I calculate that, I will get 2.28. So the 2.28 is greater than 2. So I can decide it as a one-way slab. One-way slab. Then we have to design this slab, a simply supported slab, in one way. Hence, slab is designed as a one-way slab. Right. So we have decided that we have to design this slab as a simply supported one-way slab. We know what are the given inputs are. Given inputs are clear span along the x direction is 3.5 meters and wall thickness is 230 mm. Live load is 5 kilonewton per meter square and a characteristic compressive strength of concrete is 15 kilonewton per mm square and yield strength of steel is Fe 415. So I can consider it as a 415 Newton per mm square. For given this input data, we have to design a simply supported one-way slab. So let us start with the steps. First step would be we have to calculate thickness of the slab. You know, the thickness of slab, or I can say effective depth of the slab. So there is a consideration, otherwise I can roughly assume based on my experiences, say I will assume the effective depth of the slab as 170. So after assumption, I will check with my original value. If this is wrong, then I will modify this value. So there is no wrong by assuming the effective depth. So I will assume here initially the effective depth is 170 mm and I am adapting a clear cover of 15 mm and I am using a 10 mm bar as a main reinforcement. So based on this data, I can calculate what is the total depth of or overall depth of the slab is. So this can be calculated by using this formula, that is small d is the effective depth of the slab, which we are assumed, that is 170, and here, so it is not a 20 here it is a 15. Clear cover, so I can say clear cover is 15 mm I am assuming, and diameter bar by 2. So here assuming the 170, this is 170 and this is 15 and 10 by 2, altogether we'll get 170 plus 15, 185 plus 5, so we'll get this is 190. So the overall depth of the slab is 190 mm. So finally assume the overall depth of slab is 190 mm. Right? From this step we got what is the effective depth is. Effective depth is 170 mm and overall depth is 190 mm. Right? With this we can start our next step. So we have to calculate effective span. As it is a simply supported slab, we have to calculate effective span along the shorter direction only, because we are providing reinforcement along the main reinforcement along the shorter direction, as we are getting maximum bending moment along the shorter direction. So for simply supported slab, the minimum of A and B are the two criteria given for calculating effective span length or effective spans along the shorter direction. The first criteria A is clear span plus effective depth of the slab. What is that? Clear span plus effective depth of the slab. So clear span already we know along the x direction, that is 3.5 meters, and effective depth is 170 mm. That will be converted into meters, 0.170. If we add all together, we'll get 3.670 meters. This is the effective span with respect to our criteria A. And here we have one more criteria, that is center to center distance between the support. What do you mean by this? To explain this, I will take a simply supported slab which is resting over a two simple support. Say assume that is a simply supported slab which is resting over a support, and this is my clear span that is given along the x direction is, so 3.5 is the clear span, right? And this is the support, and the width of the support given is 230 mm, so I can write 0.23, right? And we have support on either side, and the width of both the support are same. But calculation of effective span with respect to our what is that condition B is the center to center distance between the support. So it is the actual width C, and the center to center of support means I have to draw a line center of this support and a center of this support. If I measure the length, this will be the center to center distance between the support. Now how to calculate this? This will be calculated the 3.5 plus half width of one side and half width of another side. Now all together that will become a full width. So that is 3.5 plus 0.23 will give me the total center to center distance between the supports. So the same thing I have done here. See here, see 3.5 meters is a clear span, and this 0.23 is the width of the support. Directly I am using 0.23. Actually it is half of this width and half of this support width, altogether one fill width. That's why I am substituting here 0.23 meters. Now finally we will get the center to center distance between support is 3.730. To consider the effective span for the simply supported slab, one-way slab, the minimum of these two criteria A and B will be taken, and A is 3.67 and B is 3.73, so minimum is 3.67 meter. So hence effective span along effective span for simply supported slab L is 3.67 meters. It is not mm, so it is like 3.61 meters, that equal to 3670 mm. So like that we can calculate effective span. Then we have to calculate the loads. So you know loads means dead load and live load. What are the loads are given? Dead load we have to calculate anyhow based on the self weight of the slab, and this can be calculated overall depth multiplied by unit width of the slab and unit length of the beam slab and unit weight of RCC. You know what is the unit weight of RCC? That is 25 kilonewton per meter cube. And here the overall depth is assumed 0.190 meters, and 1 meter width we have considered, and 1 meter length consider, and 25 is the unit weight of the concrete. If you multiply all together, we will get the value is 4.75 kilonewton per meter as our dead load. And live load given the problem is 5 kilonewton per meter. If we add this dead load and live load, we will get what is the total load is. So the dead load is 4.125 and live load is 5. If we add all together, we will get 9.5 kilonewton per meter as our total load. But we have to enhance this load by using some factor of safety, partial factor of safety, that is called 1.5. So this 1.5 multiplied by total load is 9.75, and if we multiply that, we'll get 14.63 kilonewton per meter, right? Kilonewton per meter. Like that we can calculate what is the factor load is. After knowing the factor load, we have to calculate what is the design moment or factored bending moment. As we are designing a simply supported slab, we can assume it as a simply supported slab, a beam of 1 meter width. It is subjected to a UDL throughout like this, right? Then the maximum bending moment will occur at the center here. That value will be this, that is WMU equal to WL square by 8. So you know already W is 14.63 and L is 3. The effective length is 3.670, and whole multiplied by 8 will get the factored bending moment or the maximum bending moment or the design bending moment, we can call it as, that is 24.63 kilonewton into meters. So after knowing that, we have to go for calculation of effective minimum depth required. So for the given bending moment, what is the minimum depth required to resist that bending moment, that we have to calculate. That can be calculating by equating the maximum bending moment to the limiting moment of resistance of a section. So the maximum bending moment, that is the ultimate bending moment, is mu, and limiting bending moment is, the limiting moment of resistance is mu limit. So if we equate these two, mu equal to k into fck into bd square is mu limit, and k value depends upon here grade of concrete and grade of steel. That k value depends upon grade of steel. So Fe, for Fe250 it will be 0.418, and Fe415 it is 0.138, and Fe500 it is 0.133. Now substitute the values of mu, k, fck and b, will get what is the minimum effective depth required to resist that bending moment. Now substitute here, mu is 24.63 into 10 power 6 by 0.138, as we are using a Fe415 steel, and grade of concrete we are using is M15. So 15 Newton for mm square is the characteristic compressive strength of concrete. As we are designing this slab with a 1 meter width, so we are getting this will be your 90.71 mm. The minimum effective depth required to resist that maximum bending moment of 24.60 into 10 power 6 will be, it is not a correct, please make it correct, round it out. It is 90.71 is the correct answer, and your 90.71 is less than 170 mm. So we are safe. But if you see that our 90.71 and assumed value of 170 mm is very much greater than minimum depth required. So providing this much of effective depth is, I think it is not economical. So we have to reduce that effective depth to some value. So assumed effective depth is very much greater than the minimum effective depth required to resist the maximum bending moment. So what we'll do, we have to reduce the effective depth as well as overall depth. So finally adapt, how much we have to adapt? Effective depth is 150 mm and overall depth is 170 mm. So hereafter the effective depth of the slab is 150 mm and overall depth of the slab is 170 mm. Why we are reducing? Because economical point of view. Only your 97.3 that mm is sufficient to resist the bending moment. As for factor of safety, we go little higher side. But if you see, almost we are providing double that minimum required. So it is not economical in my point of view. So I am reducing the section. So nothing happened. We are reducing from 90 to 150. So it is a moderate value. So it is not too much higher cost or too much lesser cost. So it is a moderate value. Right. Next we have to calculate, after knowing the effective depth and the width of the slab, we have to calculate what is the area of steel provided in the slab. So the area of steel provided in the slab can be calculated by using this formula. What is this formula? Mu equal to 0.87 Fy AST D into 1 minus Fy AST by Fck into Bd. and here ME is already we know that is 24.71 to 10 power 6, and 0.87 grade of steel used is 415, and AST we have to calculate here, and effective depth of the slab we have finally we have adapted is 150, and remain and FCK is 15 Newton for mm square, and we are using 1000 mm width, and effective depth is again 150. After solving this, we'll get one quadratic equation. For solving that quadratic equation, we'll get the final area of steel will be provided is 510 mm square, or 510 mm square in the one-way simply supported slab. Then we have to check this reinforcement with respect to our minimum area of reinforcement provided. So the minimum area of reinforcement provided for Fe415 steel according to code IS 456-2000 is, that is 0.12% of gross cross-sectional area. So here 0.12 by 1000, initial area of I am taking here, that is 170, and area of AST minimum provided is 220.228 mm square. You can place like this, or you can make it to our finally adapted 170 mm also. Nothing wrong. Say this is 170 mm square, and calculate accordingly what is that area. Say. So our AST minimum is very much lesser than our AST provided, so hence we are safe against the minimum reinforcement provided. And now we go for what spacing to be provided. For the spacing provided, as we are deciding that we have to provide 10 mm diameter bar, the spacing for this 10 mm diameter bar can be calculated by using this formula, that is S equal to small AST by capital AST into 1000. Here small AST is area of one 10 mm diameter of bars, that equal to 78.5 mm square. Now substitute the values of small AST and capital AST, we will get that spacing will be 153.92 mm. So, and this value we have to check with our IS recommendation. So for spacing point of view, what is IS 456-2000 is given? For the first condition is 3D and second condition is 300 mm. If you multiply 3 into 150, you will get 450 mm, and second is 300 mm. The minimum of these three value will be provided as a what? Our spacing. So here 153, 450 and 3 mm, and lesser value is 153.92. So hence provide 10 mm bars of 150 mm center to center, because this value I am rounding up to 153.92, rounding up to 150, right? And here in the slab, the alternate bars are bent at L by 7 from the face of the support. This point to be remember. How much from the face of the support? Overall for effective length of bar we have to bent up L by 7, right? So then distribution reinforcement you have to provide along the y direction. So for this, the code has given one recommendation that the distribution reinforcement will be provided minimum reinforcement, that is for Fe415, the area of minimum reinforcement will be provided is 0.12% of overall cross sectional area. So this is gross cross sectional area is here. See, this is 150. I think gross overall depth is 170 mm here, and 0.12 by 100 into 1000 into 170 mm. So we'll get AST minimum somewhere around 200 mm or 198 mm square, and we have to provide the distribution reinforcement bar diameter is lesser than the main reinforcement diameter. For the main reinforcement we will provide a 10 mm dia, and for the distribution reinforcement here we are providing 8 mm diameter spacing bars. For that we have to calculate spacing. Same formula we have to use, that is S equal to small AST by capital AST into 1000. Small AST here is 1 8 mm diameter bar area, and if you calculate that, the 50.24 will be the small AST value. Then substitute here small AST and capital AST value, will be get the spacing will be 253.73, and this value we must check with our IS 456-2000 provisions. The for distribution bar the spacing must be maintained. 5D is one option, another is 450, and minimum of these three value will be provided as a spacing for that. Now if I calculate with the 5D, that will be 720, and for 450 another one is 253.73. The minimum value is 250.73. Hence provide 8 mm bars of 250 mm center to center. So next go for check. That is all about design of one-way slab, one-way simply supported slab. Let's go for check for deflection. That is, for this we have to calculate percentage of steel. and Fs value. Fs is what? The stress in steel under the service load, that can be calculated by Fs 0.58 Fy into AST required by AST provided, and percentage of steel can be calculated by formula. Say this is 100 AST provided by BD. So 100 AST is 100, AST is 510, and B is 1000 mm, and D is effective depth. If we calculate that, we'll get the percentage of steel provided is 0.34 percentage. And by according to this formula, we can calculate what is our Fs is. After substituting the values in that formula, we'll get Fs is 240 Newton for mm square. Now start calculation. So if your slab said to be safe against the deflection, then it must be satisfied this value. What is this value? L by D maximum must be greater than L by D provided. So we have to calculate first what is the L by D maximum is. L by D maximum equal to basic value into KT. For simply supported slab, generally the basic value be considered as a 20, and KT is a modification factor. This value is depends upon percentage of steel provided and your Fs value. So let us see obtained Fs value and percentage of steel obtained, calculate the KT value. So the percentage of tension reinforcement is here. So that almost we are getting 0.34. So it is 0.2. I think 0.34 is here. And if you project this into your go straight exactly vertical and project it onto your 240 Newton per mm square curve of Fs. So this will intersect approximately here. The corresponding value is here 1.4. So approximately assume your factor of that is modification factor KT equal to 1.4. Now calculate L by D maximum. You know the formula basic value into KT. Basic value is 20. KT is 1.4. We'll get 28 is the maximum. Now L by D provided you have to calculate. So L effective is 3670 and effective depth is 150. From that the ratio of this is 24.5. So 28 is greater than 24.5. Finally I can say our L by D maximum is L by D provided. Hence it is safe against the deflection. Similarly calculate, we have to check our slab whether it is safe against the shear or not. So for the simply supported slab, the uniform subjected to uniformly distributed load, the maximum shear force will act at the supports. So if we calculate for this case, the when a simply supported slab is subjected to UDL like this, then here we have that the support the shear force WL by 2. So this concept you have learned in your shear force and bending moment topics. So substitute those values corresponding W values and L values in this equation, that is BU equal to WL by 2. So if W is the factor load and L is the effective length and by 2, then we will get the shear force is 25.60 kilonewtons. Right? Then calculate nominal shear stress. This can be obtained from the formula VU by BD. It is given in IS 456 2000 in class number 40.1. So the substitute the values. VU is 26500. Again it is not correct. We need to multiply this with 1000. Already we have converted into the newtons. Right? By 1000 into that, then we'll get our tau V will be 0.17 Newton for mm square. Sorry, it is not a Newton for mm square. It is in terms of shear force. So it is in terms of it is stress. So Newton for mm square only. Sorry, 0.17 Newton for mm square tau V value. That nominal shear stress. Then we have to calculate the maximum tau C max. That is depends upon the grade of concrete. So in this concrete we are using M15. In this design we are using M50 grade of concrete. Corresponding tau C max is 2.5. Slab said to be safe against the shear. It has to satisfy this condition also. That is tau V is less than tau C max by 2. Hence our tau V is 0.17 and tau C max by 2 is 1.25. So our tau V is less than tau C max by 2. So hence we can say shear with respect to one condition. We have to check another condition with respect to shear also. That is tau C must be that your tau V less than or equal to K times tau C. And this tau C value can be called it as a design shear strength. It can be calculated by using the percentage of steel provided at the support and grade of concrete. So here grade of concrete is usually is M15. It is not M20. It is M15 right? The percentage of steel at support is, at the support we have to bend 50% of bar. So main bar passing through the support is only 50%. So that will be half of the area of steel provided. That is 510 by 2, that equal to 255 mm square area. And corresponding to that, if we calculate that, we will get 0.17 percentage of steel, and for 0.17 percentage of steel and M15 grade of concrete. So we are using in this problem just M15 grade of concrete, and my steel percentage is 0.17, grade of concrete is M15. Corresponding that, I have to calculate what is that tau C is. By interpolation, by interpolation technique, we can calculate tau C is 0.35. Here see, our value falls between this value and this value. In between that we have our tau C value. So 0.35 is in between, for this case 0.25 and 0.35. So almost we are getting 0.35 value tau C, and this value must be multiplied with some factor K. K is some factor given in 40.2.11 of class of IS 456 2000. This value will be depends upon overall depth of the slab. So our slab depth is 150 or less. So we are providing effective depth is 150. So take so it is overall depth, as we are using overall depth, our slab is overall depth is 170. So but roughly I am using 1.3 for the K value, and if multiply that we will get the K value 0.41 Newton for 0.41, and this 0.41 must be multiplied with our tau C, then we will get 0.41 Newton for mm square, and finally we'll get 0.455 Newton for mm square is our K times tau C. Now our tau V is 0.178 and K into tau C is 0.455. So it is greater than that. So our condition is satisfied. Hence we can say our safe in shear. Right? So let's check the development length. So development length must be fulfill this criteria, that is LD must be less than or equal to 1.3 mm by VU into L0, and here LD can be calculated for your grade of steel 56.5. I am using say that the 560 mm. It is a 560 mm, and according to this, if we calculate our what is it? Factor, that is 1.3 m1 by v into L0. L0 I am considering, I am not providing any hooks, so the anchorage length will be 0. According to this, I will get 684. Hence our LD is less than m1 by v into L0. So it is safe against the development length also. I have checked but development length consideration also. So let us start our two-way slab example. A two-way slab, here we have to design a two-way slab for a room of 5.5 meters and 4 meters in clear size, and supported superimposed load of 5 kN per meter square is 0. Acting on that, use M15 grade concrete and Fe415 steel, and the width of the support will be considered as 300 mm. So this problem can be solved. The same problem may be used for design of edge simply supported, corners are not held down, and edge simply supported, corners are held down. So in this lecture I am discussing only the first case A, and the second would be a homework for you. Please try to solve, as already we have discussed that I have designed the problem based on design the two-way slab based on this condition, and now you design by your own for this particular problem. But in this problem I am going to explain only condition A is. So let us start our prop design of this. So these are the inputs are given. The clear span along the x direction is 4.3, clear span along the y direction is 5.5, and live load is 5 kN per meter square. FCK is 15 Newton per meter square, and Fy is 415 Newton per mm square. So let us start. As for assuming effective depth, our Lx is greater than 3 meters and live load is greater than 3 kN per meter square. So we have to assume our overall depth, that is allowable Lx by D ratio, same as one-way slab. So what is the condition? Stiffness consideration for choosing the effective depth for one-way slab, that L by D ratio must varies from 25 to 30. For in this case I am assuming a 30 is my basic value. According to that I am calculating what is the effective depth. It is assumed only. So small d equal to our Lx is 4000 and our basic value I am assuming is 30. From this I will get 133 mm. Say I am provide effective depth equal to 120 mm. Based on this you have to calculate the overall depth is. For this I am assuming clear cover is 15 mm. I am using 10 mm bars. So substitute here overall depth equal to effective depth plus center to center distance between that is clear cover plus 5 by 2. Effective depth is 120 and clear cover is 15 and the diameter of bar used is 10, that is 10 by 2. If you add to all together, we will get the overall depth of the slab is 140 mm, that is capital D, right? So this is how we calculate the effective depth, and then we have to calculate our effective span along the x direction and y direction as we are designing a two-way slab. So effective span in x direction is calculated clear span plus effective depth of the slab, clear span along the x direction, and center to center distance with the support. So the clear span along the x direction is 400 and effective depth we are assumed is 120. The finally 41210 is the effective span length along the with corresponding to our condition A, and condition B center to center distance with the support. This will be the clear span plus one full width of the slab supporting the slab support width, that is 4000 mm plus width of the support is 300 mm, we will get 4300 mm. So minimum of these two value will be considered as the effective span along the shorter direction, that is Lx, that is 4120. So in terms of meters, 4.12 meters. Similarly calculate the effective span along the y direction, that is same formula, that is along the clear span is 5500 and effective depth is 120 and 5620 is the with respect to criteria A, and along center to center distance support, that is 5500 300 mm, and if you add together we will get 5800 mm. Hence effective span Ly equal to 5620 mm, then it will be 5.62 meter. The minimum of these two value will be considered. Minimum of these two values is this, right? And now we go for calculation of our loads. Here only a dead load and live loads are given. Dead load nothing but your self weight. This will be calculated capital D multiplied by unit weight of RCC, as we are designing considering 1 meter square of area of the slab. So the overall depth is 0.140 and the unit weight of concrete is 25 Newton per meter cube, and finally we will get the load is dead load. The dead load is 3.5 kilonewton per meter square. For meter square area we are getting 3.5 kilonewton per kilonewton of dead load, and live load given is 5 kilonewton per meter square. If we add together we get the total load, that is 3.5 is the dead load and 5 is the live load. Altogether we will get 8.5 kilonewton per meter square, and this total load must be multiplied with the partial factor of safety, that is 1.5 into 8.5 will get 12.75 kilonewton per meter square. So this is how we calculate our factor load. After knowing the factor load, we have to choose what condition of slab is. Slab is resting over 4 simply supported and all are discontinuous edges. So based on that we have to calculate what is our bending moment coefficients are. So as we are designing our slab with corners are not held down condition, the bending moment coefficient are calculated with respect to the table number 27, right? As per IS 456 2000, when 4 sides are simply supported, and where in our problem our 4 sides are simply supported. So this alpha x and alpha value y values are depends upon our Ly by Lx ratio, and our Ly by Lx ratio in this problem, so somewhere we are getting Ly by Lx ratio is say 1.36 and which is less than 2, so we have to design it as a two-way slab. So our for 1.36 we don't have a direct value, but for Ly by Lx for 1.3 we have alpha x and alpha y values, and for Ly by Lx ratio 1.4 we have alpha x and alpha value, but our value falls in between these. So our value of alpha x here and our value of alpha y here, by doing interpolation technique we can calculate what is our alpha x and alpha y value is. So after interpolation you can calculate alpha x equal to 0.096 and alpha y equal to 0.053, and we can calculate mx by using this formula, that is alpha x w lx square. If you substitute the values, alpha x is 0.096 and w is 12.75, and effective span length along the x direction, shorter direction, is 4.12. Finally we will get the mx equal to 20.80 into 10 power 6 Newton for mm, and Newton into mm, sorry, not per, it is Newton into mm. Along the my means maximum bending moment along the y direction. So these are the bending moment values we are calculating in a mid-span region. What is that? The mid-span region, the middle strip region of two-way slabs. And My is alpha y w into Lx square. Alpha y is 0.053, w and Lx is after multiplying this, we'll get 11.50 into 10 to the power 6 Newton into mm. So after that, we have to calculate minimum effective depth required. So that can be calculated by using by equating our ultimate, the maximum bending moment value to the limiting moment of resistance. Here we have two bending moment values along the x direction and y direction. Which value we have to take it as a mu? Here mu must be greater value of mx and my. So if you see mx and my value here with respect to this problem, our mx value is greater than my value. So in place of mu, we have to substitute mx value and calculate what is the minimum effective depth required. So by using this formula, we can after rearrange the terms, we will get this formula and substitute the values. In this, we will get small d equal to under root of 20.8 into 10 power 6. And this is a factor k value 0.138. It depends upon the grade of steel. As we are using grade of steel is to Fe415, and the grade of concrete is Fe 15. So 15 Newton for mm square is the characteristic compressive strength, and it is 1000 mm width of the slab. And finally, if you calculate, we will get 100 mm is the minimum depth required to resist the maximum bending moment, and our assumed is 120 mm. So it is sufficient. It is not more than too much more than our minimum depth required. Hereafter, we have to provide our effective depth is 120 mm and overall depth will be 140 mm. We go with our assumed overall depth and assumed effective depth here. Next, calculate the area of steel in longer direction. So we have to calculate ASTX here. ASTX means what? ASTX. This is ASTX means area of steel provided along the x direction in middle strip region, and the width of the middle strip region will be calculated by using 3 by 4 of Ly, that will be 4.215, and we have to calculate area of steel ASTX by using this formula, that is 0.87 of ASTX into D. 1 minus, it is not here, this is not correct formula, and your 1 minus would be here, right? 1 minus Fy by ASTX into FCK into VD. Now substitute all those values here. From that we will get a quadratic equation. If you solve the quadratic equation, we will get ASTX equal to 861 mm square. Similarly, for this we have to calculate spacing. As we are using 10 mm bars, spacing can be calculated by using this formula, that is S equal to small AST by AST into ASTX into 1000, and here small AST is the 110 mm diameter bar, that is 78.5. Now substitute AST and ASTX values, will get spacing 91.17 mm, right? And as this conform with our IS 456-2000 recommendations for male steel, it should not be more than like this 3 into D and 300 mm. But among these three values, we have to choose as a minimum value. The minimum value is obtained value, that is 91.17. That is, I am rounding up to 90. Hence, provide 10 mm bar of 90 mm center to center. And similarly, along the y direction, longer span direction, we have to calculate, and a middle strip width along the y direction is 3/4 of Lx, that will be 3.09 meter, and effective depth is effective depth equal to effective depth along the x direction minus diameter of bar, that is 120 minus 10, which is the 110 mm. So the substitute the values of all those things in this formula, that is My equal to 0.87 Fy AST y we have to calculate here, and D dash is effective depth along the y direction into 1 minus Fi AST y by FCK dBd. Finally, we will get a quadratic equation. After solving that quadratic equation, we will get AST y as 499.88 mm square. For this also, you have to maintain the spacing. You have to provide the same diameter of bar along the y direction also, and spacing will be calculated along this by using this formula. There is small AST by capital AST y here, capital AST y into 1000, and now substitute small AST and capital AST y, and 78.5 by 499.88 whole multiplied by 1000, we will get 157. And another condition that has to satisfy based on the IS 456-2000 is 3D and 300 mm. If we compare these three values, the minimum value will be provided as spacing for this. Among these three, the minimum value is 157. Hence, provide 10 mm bars at 150 mm center. So center, just 157. I'm rounding it to 150. Nothing, no problem. For that, we can reduce that. So the number of bars will be more. No problem. And then we have to calculate area of edge strip region. As I already told you, we have to divide our total slab into middle strip and edge strip regions, and in those regions we have to calculate area. The minimum area of reinforcement provided in the edge strip is as per code, that is FE415 we are using, that is 0.12% of BD. Right here, this overall depth, so we have 140 here, I think 140, and if you calculate that, area will get is 144 mm square, and we are using 10 mm bars in this region also. So calculate spacing with respect to this, will get 545 mm, but it is too much higher. So we go according to IS 456, the spacing will be 5D and 450. The 5 into 120 will give the 600, and 450 another minimum of that, that is 545. This is 600, it is a 450, so 450 is the minimum, hence provide 10 mm bars as 450 mm center to center. Now go for check again as this. For a deflection, for knowing this, we need to know percentage of steel reinforcement provided. That can be calculated 100 AST provided by BD, that is 100 into AST is 861, B is the 1000 and D is the 120, then we'll get 0.717 percentage. And Fs can be calculated by using this formula. This is provided in our code also. If you substitute the value of Fi AST required and AST provided, we will get Fs equal to 240 Newton for mm square. And if your slab set to be safe against the deflection, then it must be satisfy this condition. What is that condition? That is L by D maximum greater than L by D provided. So L by D maximum can be calculated equal basic value multiplied by KD. KD is the modification factor. This value can be obtained by percentage of steel known and Fs value known. Say our percentage is 0.7, it is somewhere here, and this value if you project onto this graph, it is 240, and you are right here, it is somewhere like 1.1. Approximately it is value obtained from this on y-axis 1.1. Now multiply this basic value with 1.1, that is modification factor, we will get 222 is the L by D max. And L by D provided is say 4120 by 120, that is 34, and C, our L by D maximum is, according to this problem, L by D maximum is L by D provided, hence I can say it is not okay, it is not safe in deflection, not safe against deflection. So we have to modify the things and we can make it our we have to make it our slab safe, right? So this is how we consider. Now we are getting not safe means again we have to redesign the section, and we can make it our safe against the deflection like that. So that's all for today's lecture. Thank you.